All right, so in skill 2 here, we're going to look at something called the natural logarithm. So we're going to get into log functions again. So I'm just going to do a quick review. So if you had some function that was, say, 4 to the x, the inverse function for that would be log base 4 of x. So 4 to the x is an exponential function. It looks like this. And then since they are inverse functions, the x and y are interchanged on the graph, which ends up making it symmetric about the line y equals x. So a log graph is going to look like that. So the exponential graph has a horizontal asymptote on this side. When it kind of flips and you interchange the x and y's, that ends up being now a vertical asymptote at x equals 0. And then this point on any b to the x graph is the point 0, 1. So anything to the power of 0 is 1. That's why that point always shows up, doesn't matter what the base is. And then in the inverse, every log then has this point, 1, 0. And that's a key point to keep in mind, because when we're solving for when a log function is equal to 0, we're going to set the inside of the log function to be 1. So that's a key point to keep in mind there. And then you might remember if y is b to the x, that means x is log base b of y. So what logs do is they say, tell me the exponent, so the answer is the exponent, on the base that gives y as the answer. So the thing in the brackets is kind of the answer in the exponential function. So what we're going to do is we're going to start to find the derivative of logarithmic functions. Keep in mind there's always domain issues with logarithmic functions. The x cannot be 0 and the x cannot be negative. So you can't take the log of 0 or can't take the log of a negative. But we're going to be working to get the derivative of these functions. And to get there, we got to learn about a special one that's called the natural logarithm. So I'm going to go over some log properties that you learned last semester. When you have multiplication inside, the log of a product is the sum of the logs. You can add them on the outside. So multiplication inside becomes addition outside. Similarly, division inside becomes subtraction outside. So the log of a quotient is the difference of the logs. This one perhaps the most useful when you have an exponent inside a logarithm like that. That exponent can kind of float down in front, and it just becomes the log base b of that number with the exponent out front. Here's just relating back to the graph. If your x is 1, your answer is 0, because this is saying, give me the exponent on b that has 1 as the answer, while b to the 0 is 1. And that just coincides with this point here. But again, if you're trying to solve where a log is 0, if you have log of stuff equals 0, you're going to set the stuff equal to 1 in order to solve that. And then just some other sort of basic logs. If you're doing log base b of b, what's the exponent on b that gives b as the answer? Well, the exponent there is 1. And similarly, what's the exponent on b that gives b to the power of k as an answer? Well, the exponent is k, whatever that is. And then the last property I wanted to go review is the change of base formula. So that was like, I'm sure you used it in this way. If you wanted to do log base 5 of 100 in your calculator, if you don't have a button that lets you change the base, you'd punch that in as log 100 over log 5. So that's, you're changing the base to, this button here is base 10 on your calculator. So that's how you change the base from base 5 to base 10. Or in general, that works with absolutely any base. You do log with the new base that you want of what it was before, and then log of the new base you want of the old base is the official formula there. but that's called the change of base formula. So with that, we're going to look at what's called the natural logarithm. So in the first lesson here, we had this cool thing where we had y equals e to the x. The inverse of that would then be, maybe I'll use my inverse notation. The inverse of that function would be log base e of x. So that's the inverse of e to the x. And since e is kind of the most important base for an exponential, because it is its own derivative, it's the one that's sort of all the other derivatives are going to come from, we'll see. So since e is the most important base for exponentials, e is also the most important base for logarithms. And so log base e is used so much that it got a special name, and it got a name of the natural logarithm. So the natural logarithm is just log base e, and there's a button for it on your calculator. It's shortened to ln. So that ln button on your calculator just means log base e. The n stands for natural logarithm. So it is just sort of a short form for log base e. That's all it means. This is still a logarithm, so it should be pronounced log still. You could say natural log or just log. Often people will say just log and they mean natural logarithms. So logarithms are a bit of a nightmare depending on which subject area you are in. When they say log, they mean different things. So scientists, when they say log, they're talking about log, and they mean log base 10. When a mathematician says log, they mean log base e, and they'll write ln. If a computer scientist says log, they might write lg with no o there, and they're talking about log base 2 because computer science, you work in binary, so base 2 is what you use quite a bit in the math and computer science. And then even worse, a statistician would say log, they write log, but statisticians are actually using the ln button on their calculator, the natural logarithm. So they say log, they write log, they don't mean base 10, they mean base e. Statisticians are weird. Okay. So I'm going to say log, but I'll mean the natural logarithm. So I'll try and be careful and say natural logarithm. Lots of people see that and they pronounce it ln because it's ln. And lots of mathematicians will get mad if you pronounce that ln. I had a professor, if you put up your hand and said, oh, you use the ln button on your calculator. He said, ln, a lawn is something you mow. So you're supposed to say log. That's my log. Blah. So what we're going to do, just so I'm not dealing with this inverse notation, I'm just going to start with this. F of x is the log of x, the natural logarithm of x, and we're going to find its derivative. And in order to do that, actually I probably didn't need to erase all that stuff, because I'm going to write it as y equals the natural logarithm of x. And we're going to find the derivative of that. And how that works, we use something to figure out the formula for this derivative. We use something called implicit differentiation, which is something that you'll definitely learn in a first-year calculus course, but it's a bit beyond what we would do in high school calculus, but I'll show you how it works. So basically what we're going to do is we're going to rewrite this in exponential form. So in exponential form, x is the answer, the base is, since it's the natural logarithm, e, and y is the exponent. And how implicit differentiation works is you take the derivative when your y isn't kind of by itself. When it's not y equals anymore, you got a y somewhere in the equation though. You're going to take the derivative and just treat y like it's some function. So we're going to take the derivative of both sides. So the derivative of x is 1. The derivative of e to the y would be e to the y. And then the chain rule says, since that's not an x, since that's a function up there, the chain rule says multiply by the derivative of the inside, multiply by the derivative of that function, which we're just going to write as y primed. And then the idea here is we've got a y prime now in our equation. We can solve for that y primed. So you get y primed is 1 over e to the y when you divide that out. And then that would be kind of a weird answer because we started with y is the natural log of x. It would be weird to have y in our answer. We're used to seeing x in our answer. But the nice thing is x is in fact e to the y. So we get this nice y primed is 1 over x. So that's kind of our formula. The derivative of the natural log of x is 1 over x. So armed with that as your new formula, see if you can find the derivative of each of these things. So you can pause, and then I'm going to keep going. So this is a chain rule 1, so because there's a function inside. So the derivative of log is 1 over x. So the derivative of log of a function is 1 over that function, and then separately multiply by the derivative of that function. And the nice thing here is, doesn't matter that 3 there, it cancels that 3, and you get right back to 1 over x. So we get this strange property with these functions where this horizontal compression inside there, so there's a horizontal compression by a factor of 3, it actually doesn't change the slope of the graph. All the slopes are the same as if you hadn't compressed it at all, which is really weird to think about. So like you take this graph and you horizontally compress it in, and what happens is the slopes stay exactly the same. You get the exact same graph, it just actually gets bumped up a bit. So when you push it in, it's like an infinite amount of rope. So the rope just keeps going down, and when you're pushing it, it actually kind of lifts up is kind of how I visualize it. The other way to think about that is using the properties, log of a product is the sum of the logs. That is just the original graph shifted up by whatever the log of 3 is. I think it's like 1.1 if I remember. You punch log 3. So it's the same graph shifted up. So log graphs have this weird property where horizontal compressions have the exact same effect as vertical shifts, which is pretty weird to think about. Okay, none of that's important. It's 1 over x. That's what's important. This one, I've got x times the log of x. So we're going to need our product rule. F prime g, so that's just going to be log x, plus g primed 1 over x times x. And again, if we wanted to simplify it, that would just turn into log x plus 1, which is kind of neat because those x's would cancel. Okay, another chain rule. Derivative of log is 1 over x. Derivative of log of a function is 1 over that function, and then times that function's derivative. And then I'm not requiring you to simplify, but the first step of simplifying would be just put that derivative now on top when you multiply those fractions, because the other fraction has a 1 on top. So there we have it. Here's another chain rule, but here it logs the inside function. So 4 comes down, you get the natural logarithm to the power of 3 now. And then the chain rule says multiply by the derivative of what's inside. The derivative of natural logarithm is just 1 over x. So we get that. And then here's a fun one. Where is the tangent horizontal for this function? So again, we're going to take the derivative. We're going to solve where that derivative is 0. So again, you can pause and try and do it yourself, and then check in and see if you're doing the same thing as me. But the 3 is going to come down, become a 2. The inside is going to stay exactly the same. And then multiply by the derivative of the inside. The derivative of the inside is a log of a function, so you get 1 over, instead of x, 1 over that function. And then we're going to have to multiply by that function's derivative, which is 2x. And we're solving where this is 0. I've got on the numerator, 3 times 2x, because that's a 2x over 1, so I'm going to make that 6x times the log of x squared minus 1 squared all over x squared minus 1. So that's what we're solving where it's 0. Since we're looking for where the tangent's horizontal, all we care about is the top of this fraction. So where the top of this fraction is 0. The bottom of the fraction would be where the derivative doesn't exist, and we'll deal with all that sort of stuff when we get to graphing and that sort of stuff. So we're not going to worry too much about that. We're just solving where this is 0, so just where the top is 0. So we get x equals 0 is one of our potential points where the horizontal tangent. And the other thing is where this is 0. And we've got this log thing equals 0. What does that mean? Oh yeah, that means that the inside has to be 1. Logs are 0 when the inside is 1. So we get x squared equals 2. So we get x equals plus or minus the square root of 2. And so I would say, where's the tangent horizontal? If I rush in and say 0 plus or minus 2 are my x values where the tangent's horizontal, I'm going to get this question wrong because log functions have lots of domain issues. Log functions don't exist anywhere where the x values are negative or 0, so we got to be careful. So we actually have to check the domain. So I'm going to check. I'm just going to call it f instead of y. I'm going to plug in these and see if I actually get points or not. And here I get the log of negative 1 to the power of 3, and that does not exist. So 0 is actually not an answer because that's not in the domain of the function. If I do f is root 2 or f is minus root 2, I'm going to get the log of x squared 2 minus 1. I'm going to get the log of 1 to the power of 3 in both cases, which is in fact a number. It's actually the number 0. It's the x-intercepts of this fun thing. So those are good values. So therefore, horizontal tangents at x equals plus or minus the square root of 2. 2 of them in this graph. So that's it for this lesson. You can make yourselves some notes. So we already wrote the important properties of the logs up above, but you can remind yourself of that. And then what's the inverse of y equals e to the x, and what's its derivative. There's also a spot for this derivative on that formula sheet I gave you, so you can work on that. Then you can take a stab at the exit card. We can talk about that in class, and then you'll have time to practice in class as well, hopefully.